Okay, good morning. We actually officially start the lesson, so we had some introduction about what the course is about somehow. But today we start section 1.1 of the PDF file that I just put on a Google Classroom. So we want to talk about mathematical proofs. Okay, so there are some statements that I want to mention here. So what is a statement? Yes. This is some terminology, of course, in mathematics. You know about statement in colloquial language, but statement in mathematics means something very specific, okay? So this is the definition of a statement. So we say a declarative sentence that is either true or false, of course, but not both, is called a statement. Okay, so I am defining the word statement in mathematics. So I can clean this and I would say this is a definition in mathematics. So when I say definition, what do I mean? I mean that I want to describe precisely, I don't know, an object or an idea or a concept in mathematics. So when I use the word definition, you expect that you will see a description in front of the word definition that describes in detail what do I mean by a word or by a concept. Yes?
What does declarative mean?
Yeah, I will tell you. Declarative means that it declares something. Do you know that I have done the spelling correct? Is that right? Declarative. Yes, it should be correct. Okay, because we have a sentence, for example, let me give you examples, it becomes clear. So it is important, I will emphasize on this word declarative here, and I also emphasize that it should be either true or false. Okay, and then usually in math books, when you read this definition, you will expect to see a word in italic or in bold or in a different color. It means that that is the description for that very particular word that you see it in italic. Okay, so in principle, if I want to respect those things, then I can say, for example, it's called a statement. Yes. So whenever I write definition in Math 3, I don't know, in Math 4, in Math 5, wherever you see, it means that I am defining an idea or a thing or a concept for you, which will be useful. So this is why, because we need to have common terminologies so that when I say a statement, when I'm doing teaching, then you understand what I mean. Yes. So I'm defining this word. So what is the declarative, and then being true or false is actually important. For example, Stockholm is the capital of Sweden. Okay, so you see, this is a statement. It declares something. Okay, it declares something to you. It might be true or might be false, but at the same time, it cannot be both true and false. Okay, so here in this say, you see, this is a sentence. It declares to you something, and in this case, it is true. We say that the value of this statement is t. Okay, so it means that this statement is true. Of course, value, when I say value, you should think about numbers, but this is also common that we want to evaluate a statement if it is true or false. We say that the value of the statement is 2 or f for false. Yes, in this case, I have a statement which is true. Yes, for example, I can say 25 is divisible by 7. It declares something to you, but of course it is false. the value of this statement is false because 25 is not divisible by 7. So that's also a statement, it is false. But when I say, for example, divide 20 by 4, what do you think about this? Do you think this is a statement? No, because it's not declaring something. This is, I think in grammar we call it imperative sentence. I don't exactly know. It tells you to do something. It's not declaring something. So, and of course you understand there is no truth or false. There is no truthness or falseness that I can associate with this sentence. This is telling you do something. Yes, it's not declaring something. Yes.
When you say that a number is divisible by another number,
Yes.
does the answer need to be an integer?
An integer, yes. We will talk, of course, about this, but I'm relying a little bit on what you have learned before. Because the next chapter will be number theory, and we will talk about these things extensively. But I hope that you understand by divisibility what I mean. But I want you to understand that this is a statement, and it is a true statement. This is also a statement, it's a false statement. But this is not a statement at all. It's not declarative sentence, so not a statement. And of course, if I say the weather is nice, what do you think about this? Do you think this is a statement or not? At least it is declaring something, yes? But do you think it's a statement or not? Yes, what is your opinion about that? Pardon?
Probably not.
Probably not. Why? Yeah, exactly. That's a subjective thing, yes? To say that the weather is nice. So we want to avoid these kind of declarative sentences, and we don't want to categorize them under the title of a statement because it is not that clear. For one person, I don't know, the cloudy weather, if you are in front of the, I don't know, fireplace, and then it's raining, might be it is beautiful or nice, and for the other person who's in rain, it's not beautiful, okay? So we want to avoid these sentences. So we cannot say this is definitely true or false. Okay, so we want to avoid that in mathematics. So we say that not a statement. Not because it is not declarative, indeed it is, but it is not clear if it is true or false. But for example, what do you think about this? I would say the number, I don't know, 1, 2, 3, 4, 5, 7 is a prime number. You know a little bit about this, yes? What is a prime number?
Number that's only divisible by itself in 1.
Yes, and a natural number, yes? A natural number greater than 1, which is divisible only by itself and by 1, is called a prime number. Okay? What is your opinion? This number that I have written here is a prime number. I just wrote something randomly, okay? So, do you think it's a statement or not?
It is a statement.
It is a statement. First of all, it declares something, and then it is either true or false, even if I don't know right now if this is true or false. So that is not something that you have to be careful about. This is a statement. You know that, for example, if you have calculator or computer or any tool, in principle, this statement, this sentence is either true or false, depending on if this is really a prime number or not. Even if I don't know right now if it is the case. So I cannot assign T or F right now, but I still know it's a statement. Yes? Okay, what about this one? X is greater than 5. Is it declarative or not? Yeah, it's declaring something, but is it a statement? Yes?
Say no,
The answer is no. Why?
because it's ambiguous. Because what's
It's exactly the same word that you're. It's not clear. When I have written x is greater than 5, it might be true or it might be false, depending on the value that I want to assign to x. So this is why I told you that a declarative sentence that is either true or false, but not both, is called a statement. So it's not a statement. But if I have a declarative sentence including one or more variables in it, like this sentence that it includes the variable x, there is another name for it. We call it a predicate. Okay, so a predicate is a declarative sentence that includes one or more variables in its statement. Okay, and of course we cannot say it is true or false because we don't know the value of x. Is that clear? That's called a predicate. But we have some tools to change a predicate to a statement. Okay, so let us keep it like this. So let me rewrite this sentence by adding a phrase to it. Okay, I would say there exists a real number x that is greater than 5. X is greater than 5. I am adding a phrase, there exists a real number x that is greater than 5. Now, of course, this is also a declarative sentence. It declares something, and it includes still your variable x. But now my question is that, is this a statement or not? Think about it. Yes?
I think it's a statement.
Yes, because this is claiming something, it's declaring something, and can you say for sure it is true or false right now? Yes, because even though it still includes the variable x, but you can immediately say it is true or false. Either this is true or false. Do you agree? Either there exists a real number x which is greater than 5. If that's the case, then this is true. Or there is no number x greater than 5, then that, of course, this becomes false. So, but in this case, is it true or false?
True.
It's true, yes. If I ask you why this is true, because everything that I'm talking about is based on logic, so you already know these things in your head, okay? So, you told me this is true, okay? If I am stubborn and I want to ask you more, and I say why this is true, what do you answer me? How do you answer me? There exists a real number x greater than 5. Yes?
If you add 1 to 5, you get a number greater than.
No, try to make it as simple as possible. What you are saying is correct. So how do you say, by the way, how do you say that this is a true statement? Yes?
Can be applied to many situations.
No, just be careful exactly. Don't say a very wide range of words or things. Be very precise. That's the whole point of this part of the lesson. Okay, so you have to be very precise in your statements, what you say. If I insist, okay, why this is a true statement, how do you answer this question? Yes?
Since 6 is a real number and x can be any real number, that means x can be 6. And since 6 is bigger than 5, then
Yeah. I would say 99% is correct, yes? You would tell me, look, Babak, do you agree that 6 is a real number? Then I say yes. Then you say that, do you agree that 6 is greater than 5? I would say yes, then you are done. Yes, as simple as that. That's not a very mysterious thing. Because here, this, by the way, do you remember I was talking about bringing an example is not good for proving things? But I want you to know that if a statement in mathematics starts with there exists, first of all, it means there exists at least. We don't write at least there, okay? So there exists, if you want to prove a statement which starts with the word there exists, with the phrase there exists, then what you need to do is to really show something exists. And to show that something exists, then you have to give me the example. Okay, so be careful. This is called a quantifier. There exists is called in mathematics a quantifier. And more explicit, this is called an existential the existential quantifier. These are big names, but this is just terminology. Existential quantifier. Yes? And then there is a symbol in mathematics for it. This is the symbol. Okay? So if I want to write this sentence in mathematical symbols, I would say there exists an x. Where this x is coming from the set of real numbers. It is a real number. If I want to show that the set of real numbers in mathematics is denoted by this symbol, R for real, and then we have an extra line around that, so we show that this is the real numbers. And then if I want to say that x is a real number in mathematics, we write this symbol. So this, how I read it, I read there exists x in real numbers, and then such that x is greater than 5. Okay? So that is the way that I write this English sentence in mathematical symbols. Yes? So if I ask you what I did, I had a predicate, a declarative sentence with a variable in it. I used this phrase in the beginning, and I turned this predicate into a statement. Yes? So that, and then this there exists, the phrase that there exists is one type of quantifiers. There is a name for it, existential quantifier, and that's clear, existential, because it claims that something exists. Yes? If you don't like these names, forget about them. But I will use these kinds of symbols in my writing a lot, okay? So you should be able to read this. So if I want to read it, this symbol means there exists x in the set of real numbers such that x is greater than 5. In this case, it's a true statement. If I ask you why, you should bring me an example. You should prove me the existence of the claim. Yes? Yes.
Do we have to use those symbols ourselves?
Pardon?
Do we have to use those symbols ourselves?
Try to use them. Yes? Okay. This is one type of quantifier, and we also have another one. Let me take the same predicate up there, x is greater than 5, and write this. For all real numbers x is greater than 5. Okay? Of course, this is a declarative sentence, and it includes a variable. But do you think I can call this a statement? Yes or no? A statement is a declarative sentence that you can for sure say there are two possibilities for that sentence, either true or false, even if you don't know which one is which now. Okay? So in that case, do you consider this a statement or not? Yes? This is a statement because it claims something, and I can say, this tells you that for every number x is greater than 5. Of course, this is nonsense. It's a false statement, but it is a statement. Yes? So this is a statement, and in this case, this is false. Okay? So I was able to, this is also a quantifier. For all is also a quantifier, and that is called the universal quantifier. Yes? And there is a symbol for it in mathematics. It's an upside down capital A. Okay, so if I want to write this sentence in mathematical symbols, I would say for all x in R, what happens? X is greater than 5, which of course in this case is false. Is that understandable? It is false. It is claiming that whatever you choose from the set of real numbers is greater than 5. Of course, this is not true. Okay, now still, if I insist you to tell me why this is false, how do you answer this falseness? How do you argue for the falseness of this statement? Yes?
Because 4 is a real number,
Mhm.
and x, if x is 4, then x
It's not
greater
correct.
than 5.
Yeah, exactly. So you see here, if it this, so let me write here. So if a statement starts with the existential quantifier, to prove we need to bring the example that it works. That works. Okay, and if you want to refute it, okay, so here, if you want to refute this quantifier, how do you do that? Yes?
You show that it doesn't work in any case.
Okay, so it means that example is not enough. Because if you bring one example that does not work, you haven't refuted anything. Yes, so that's important. If you want to prove something that starts with this symbol, it is enough to bring an example that shows it works. Yes? But if you want to refute a statement that starts with this symbol, you cannot say that, okay, even if you bring hundreds of examples that shows does not work, it's not enough. You need to have an argument to show why no one can even find one single example. So here you need to refute, you need an argument. A valid argument, of course. What is the name of the valid argument in mathematics? A valid argument in mathematics is called proof. Yes. So you need a proof. Okay? But can you now, the same thing, I want to write this universal quantifier here, and I want you to write some sentence in front of it. If you want to prove a statement starting with this quantifier, what you are supposed to do? Everyone? Do you understand what I mean? Because we have sentences, we will use these things a lot in mathematics. There exists and for all. If a statement starts with there exists, if you think it is wrong and you want to refute it, you need to have a valid argument. If you want to prove it, it is enough to bring an example that shows it works. I want to write the same scenario for the universal quantifier. If it claims something is true for all, if you want to prove it, what do you need? Yes?
You need a valid argument.
Valid argument. Here, to prove, we need to bring, so we need a valid argument. Okay? But if I want to refute it, this claims that this works for every case. If I want to refute it, I need to bring one example that shows no, this is not the case that it is working for all cases. At least it does not work for this case. Yes? So then to refute, another English word that we use is rebut, yes? Is to refute. To refute what we need to do, we need to bring an example. We need to bring an example that, can you complete it? Can you complete the sentence that?
Does it work?
Doesn't work, yes. It is in summarized word. I'm just trying to write something that in the future, if you want to refer to it, you have something to refer, okay? But it's easy for you to understand. Yes? For example, this is an example in the book. Some of the examples are actually good, so let me just use that. I intentionally I want to write it in the mathematical symbols, not because you have to write everything in symbols. No, it is. I myself prefer to write a lot of sentences. I will show you research papers in mathematics that you have to write sentences, okay? Okay, but let me write it because I want you to get used to it. This is the example in the book, so let me just exactly use that. But I want you to understand, to read it for me. So let me just write some symbols for you. So the set of natural numbers in mathematics is denoted by this symbol. The set of natural numbers means the set, of course, in American school we start with 1. In European school we start with 0. Okay, let me start with 1. 1, 2, 3, 4, 5, etc. So this is the set of natural numbers. You should go from the other direction, yes? Yes. Yeah. Yes? So this is the set of natural numbers. This is coming from the set of natural numbers. Is the German word Zahlen for number or something like that? But here, we use in English, we say integers. Or Heltal, you say, yes? So this is the set of integers. So what is this? So we have negative numbers, -3, -2, for example, up to -infinity, -1, 0, 1, 2, 3, and etc. The set of integers. Yes? And sometimes I use this symbol. This is also common. For example, I can write Z, and then I put a positive sign on top of that. So I mean, consider the positive ones. But of course, the positive ones in this case will be the same as n. Okay? But sometimes I write Z. There are different symbols people use. I put greater than or equal 0 on top of that. So it means that I am considering all numbers that start, integers that starts from 0 onwards. Okay? So these symbols that I'm using are universal. Everyone uses it. But these things depends on the author of the book or the article that you are using. Yes? Okay. So let us, for the time being, stay here. So here, this is the example 1 in the book. So I want to write it in this language that I described for you. How do you read it? Okay. So how do you read this if you want to read it in English? So try to read it in plain English as much as you can, yes. How do you read these symbols here? The book hasn't used the symbols, the book has used the letters and words. But what is the meaning? Do you understand what it means by looking at it? Yes, do you want to read it for me?
There exists A and B in a set of all natural numbers, so that 2AB equals A squared.
A squared. Okay, but if you want to translate it in plain language, so you don't only say there exists A and B in. So you say that there are natural numbers A and B such that 2AB is equal to A squared. This is a better way of reading, but that was completely fine. Is that clear? So by looking at this, you need to understand what does it mean. It means there are natural numbers A and B, so that 2 times A times B is equal to A squared. Is it a statement or not? Yes? It's claiming something, and it is either true or false. Yes? Okay, now what is your feeling? You should have some kind of intuition or feeling in mathematics. Because if you believe this is true, this starts with this symbol. And if you want to prove this symbol, you need to bring an example that works. If you feel this is false, so you want to refute it, and if you want to refute, you have to have a valid argument. Okay? So then you have to decide at this point, do you think it is true or false? Because if you think it is true, you have to bring an example. If you think it is false, bringing examples are not enough and good. You have to have a valid argument. So first you have to decide, and this is not easy, by the way. Do you remember I talked about the Fermat's last theorem? It was not clear, is it true or false? So anyway, which one do you think it is here? Is it true or false? And tell me why. Anyone else? Just, yeah. It's very simple, okay? The examples in this chapter are not because they should be hard to calculate or something, because they want you to understand these concepts. I want everyone to actually participate. Anyone else? Say something, even if it's wrong, that's good, because we learn together. Yes?
It's false.
It's false. So you want to refute it, yes? Then you have a harder work to do. You have to have a valid argument. So, do you agree that
For that,
for this existential, so here you see, you said it is false, or yes? So when you say it is false, it means you want to refute it. You want to say it is not correct. Refute means saying that something is not correct. And then you need a valid argument. So it is not enough to give me some examples. You should convince me, Babak, that no matter how hard you work and how hard you look for numbers there, you will not be able to find two numbers A and B so that 2AB is equal to A squared. Yes? Okay. You want to answer?
Me.
Yes?
This question.
Yeah. Oh, I thought that you want to answer because you raise your hand and then put it on your head. So I thought that you want to answer. Okay, no worries. Yes?
So do you want us to refute this
I
argument?
don't know. That's up to you.
Okay, can I try refuting it?
So you want to refute it.
Yes, I want to.
So if you want to refute it, you need to
Okay,
give me a valid argument.
but if you rewrite it and you say the square root of 2ab is equal to a,
What?
but if you want to like rewrite it to square root 2ab equals a,
Yes.
then it has to be a bigger number. And b can't be a negative number because it can't be a negative square root.
No, not because of that. Because I have excluded the negative numbers from my domain. Okay. Then what? Okay. So are you convinced that you refute something? That's exactly what I'm saying. By the way, this mathematics works based on logic in our head, and probably logic is a little bit biological. So the human brain has evolved in that way. Okay, this is not something that I'm teaching you. I'm trying to draw your attention to logical thinking. Okay, not because you don't have logical thinking. You already know the logical thinking. We are training on that. So what you said is nothing. Yes, is some kind of scratch work that might give rise to a valid argument. Okay, but you haven't done that yet for me. Yes, you're loud thinking. That's not the problem. I want you to understand, because if a problem is hard, I myself don't know what to do. Okay, I will try to check two strategies. One strategy for refuting, one strategy for proving. And at the end, I don't know which one will work. If the problem is hard, I showed you before, it took 300 years people to prove that conjecture. Okay? So for the time being, let us review those words. If you don't have a valid argument for this is just a conjecture for the time being. Yes, we don't know. This is a statement. It might be true or might be false. Okay? Yes?
The statement is true.
The statement is true.
Yes.
So when you say true, it means that you want to prove it.
Yes.
So it means that you need to bring an example that works.
Yes.
Okay? Okay. Can you bring an example for me that works?
Okay, so if a equals 2 and b equals 1.
Okay. Is he allowed to choose these two numbers? Yes or no? Why?
They're natural.
Because this is the assumption. The numbers should come from the set of natural numbers. So what he is choosing at least is valid. But let us see what happens in the future. Okay, then
And then
if you choose A, 2A and B, and then you calculate 2AB for this choice, it becomes 2 times 2 times 1, which is 4. And if you calculate A squared, which becomes 2 to power 2, which is also 4. Are these two numbers equal now? Yes. So we prove this is true. Yes, it is true. So we wanted to prove this. I need to bring an example that shows it works. And you were able to bring an example that it works. Is this example in this case unique? By the way, the hard problems are that the example is sometimes unique. You have to be so clever to find that one very single example. But it was not in this case. For example, now that you understand what is going on, can you cook up another example for me here? Because when I say there exists, implicitly I mean there exists at least. So if you provide one, it is enough. But sometimes you might ask yourself harder questions. Can I cook up another example that shows that it works? Yes? A is equal to?
4, B is equal to 2.
E is equal to 2. Let us check. So 2A times B becomes 2 times 4 times 2, which is 16. And then, yes, A squared is also 16. So if I give this in the exam and I ask you, tell me, is it false? Or I will ask the question like this. You will see the question. Okay, which one of the following statements is true? Which one is false? Motivate your answer. Okay, so if you see this as one of the statements, you should write in this way. This is true since, for example, A is 2 and B is 1 are natural numbers and they satisfy this equation based on the following calculations. That's it. Yes? Are you feeling okay or not? Yes? Are you happy? Are you understand what's going on? Okay. So this was the example in the book. Okay, we learned a little bit about trigonometry yesterday. So this is also an example in the book. So how do you read it? For all theta, okay? Let us write it in words. Theta is a trigonometric angle. For any theta, let me write it in this way. For all, by the way, you can also write for any. They mean the same thing from English point of view. For all trigonometric angles, for all trigonometric angle theta, if sine theta is rational, then sine theta over 2 is rational. This is also an example in the book, so I'm just using that. Do you know what a rational number is? A rational number is a number that can be written as a fraction so that A belongs to the set of integers, B also belongs to the set of integers, but of course B cannot be equal to 0. That is called a rational number. For example, 2 over 3 is a rational number. Yes, it's a fraction. The numerator and the denominator are coming from the set of natural integers and the denominator is not equal to 0. Yes, there is one famous non-rational number, irrational we call it. Non-rational, we don't say it in English, we call it irrational. Okay, there is one famous irrational number. It means that, what is that number? How do you know that a number is rational or not irrational? There is a good indication sometimes. Yes?
The indication would be that the digits of the decimals keep going forever.
Okay, yes, that's right. Okay, but I don't want to make it so complicated. Can you give me an example of an irrational number, very, very famous one? Yes?
I.
No, I is too much. So I just want to, I is not in the real numbers. Okay, we will talk about that in the last chapter of Math 4. But just give me an example of a number which is not rational. Yes?
Pi.
Pi is a good example. Yes? Pi, but no one knows why pi is irrational unless you have a proof. And mathematicians has shown that there is a proof for that. Pi is a famous irrational number. It means that no one can find two numbers a and b so that when we write this fraction, it becomes exactly pi. Okay, for example, you might write this fraction. So what is the answer to this? It is 3.14, but this is close to pi, but it is not pi. Okay, so mathematicians have proven that this is not possible to find any fractions of this type whose answer is exactly pi. So then it means pi is irrational number. So remember, this information is good to know. There is also one famous irrational number, probably you learned it in Math 3 CS. What is this number? E? Do you remember? It's Euler number, the Euler number, yes? So this is also 2.7 something, yes? You learned it in math. So do you remember when you want to take the derivative of e to power x? E, what is this number, the Euler number? So these are very famous irrational numbers. Another very famous one, yes?
Does that have to be famous? Like
I mean, yeah, so say whatever you want to, yes.
square root of 2?
Yeah, that's also famous, yes. So the square root of 2. This, we will be at the level to understand why square root of 2 is irrational. But for proving pi and e are irrational, you have to know university mathematics. But for square root of 2, in this course, we will show you why square root of 2 is irrational. Okay? But an indication of an irrational number is this sign. In mathematics, this sign is called a surd sign. Some people call it radical, that's also correct, but this is the word surd, okay? So if I have a square root of 3, square root of 5, these are irrational numbers, yes? This is good to remember. Okay, now let me clean this, because this is important for in this example. Now, this is the claim. First of all, let us review. For all trigonometric angle theta, if sine theta is rational, then sine theta divided by 2 is rational. Okay, first of all, independent of if you can prove it or not, do you agree with me this is a statement or not? Yes? It is declaring something. It declares that if sine theta is rational, sine theta divided by 2 is rational for any number, any trigonometric angle, for every trigonometric angle. Now, this is which quantifier? This is this quantifier. Okay? Now, again, you have to have a feeling. If you think it is true, what you need to do? You need to bring a valid argument this time. If you want to say, no, this is false, what you need to do, you need to bring an example that doesn't work. Okay? Again, that is up to you to decide. Do you think it's true? Then the burden of proof is on you. If you say no, then you have to show me an example. That does not work. So which one do you think is going to work here? It depends to your memory. I did it yesterday for you. Do you remember I filled up a table for you? There were some numbers there. So this is the nature here. So if you don't, I don't know, there is only one way to do this, and that is what I'm going to tell you. And that's the problem. So this is the matter of life or death. Either you solve it or you just don't solve it. So I want you to understand there is nothing that you can cook up in the middle and I accept it with you. If there are 2 points for it, either you solve it completely, you get 2 points, or you lose all of it. There is nothing in between. I want to understand black and white. Okay, first of all, what is your intuition? Do you think this statement is true or false? You have to have an intuition, because otherwise you don't know on which feet to work. Yes? You want to say it is false. If you want to say it is false, then this goes to this category, and then it means that you have to show me an example that does not work. Okay? So what is that? Did you come up with that example?
Sine of 90 is equal to 1,
Yes?
but sine of 45 is equal to a number.
Exactly. So that's the one example, yes? So he's saying that he wants, first of all, to refute this statement. To refute this statement, he should provide an example that does not work. And for that example, he chose how he could come with that, we don't know. Because that is, you need to go to his brain and see how he did. And then by practice, you need to also be able to do something like that. Is that clear? There is nothing that I can teach you here. I can explain his argument and you will understand. But the point is that at the end, you have to come up with that intuition yourself. Okay? So what he is saying is that, he is saying that I want to refute this. This is first of all his intuition. To refute this, he knows this rule, so he should provide an example that doesn't work. And for his example, how I don't know, we have to be in his head, he chose this number. Yes? And now the rest of it should be easy for you. So how can you say that this is the good example? Because if I ask you, you need to calculate sine theta for that angle, which becomes sine of 90 degrees. If you imagine that unit circle, this is one of those angles that you can immediately understand. Do you remember? It is the y-coordinate of the point for 90. 90 is on top. What's the y-coordinate? 1. Yes? And then you also need to calculate sine of theta divided by 2. So theta is what? Is 90 degrees divided by 2. But 90 degrees divided by 2 is also an angle, which is 45 degrees. And then, do you remember, I told you, remember at least these angles are famous in trigonometry. So 45 degrees is one of those famous angles. You put the table in front of you, even in Math 5, you have access to it. So then what happens? It becomes what? 1 over square root of 2. So, if you don't remember it. Okay. And now, do you agree now that this is an example that shows that this is not correct? So this is called a counterexample. A counterexample that we use to refute. By the way, let me write. We need to bring an example. This example is called a counterexample. Okay? So this is the counterexample. Do you agree that this is a good counterexample? Why? Because sine of that angle is 1. Is 1 rational or irrational?
Rational.
Is rational, because 1 can be written, for example, as 1 over 1. 1 is rational. But for the same angle, when I calculated sine of theta over 2, I got this number. Is this number rational or irrational? Irrational. This claims that if sine theta is rational, sine theta over 2 is also rational. But this claim is refuted here. Because we were able to bring an example for which sine is rational, but sine theta over 2 is not rational. So we are done. Yes?
Is irrational number with infinitely many decimals?
Yes, it means that exactly. So for example, if you have a square root of 2 in the calculator, it will fill up the display. And if I make a monitor bigger, it will fill up my display, and if you have the cinema, it will fill up the cinema, so it will not end. That's the meaning. But of course, you might ask the question, Babak, how do you know that this will not end? Might be if I have a very, very, very huge display, at the end of the day it will finish. And that's exactly the power of mathematics. The power of mathematics tells you that no matter how we are able to make big displays, no matter how big that display is, it will not be able to cover all the digits. So that's a very big claim. Then we have to have a good argument for it. Yes? Is that clear? By example, we can. So in other words, what you said is correct. This is one property of irrational numbers, that the decimals will not end. That's one way to see the rational numbers. But is this understandable? So, but this example in the book. So when I say that, okay, do you think this is true or false? If it is true, prove it. Or so I would say, if this statement is true or false, motivate your answer. Then that's up to you to decide. Okay? So you have to train yourself for this. Okay. And then, for example, here, let me give you another example that's also in the book. I don't want to deviate that much in this course because I don't want to stress you out. But you need to start training. It's not that hard. In the beginning, because it needs a little bit of different thinking, you might think it is hard, but it is not. By the way, you see that the algebra is even simpler than Math 4. Algebra is actually nothing. Yes, so you need to train yourself in this case. Okay. So, what about this? Can you write this for me? Let me ask you, by the way, one question. A plus b to the power of 2 is equal to a squared plus 2ab plus b squared. Okay? My question is that, do you think it's a statement or not? I just write this for you, and I ask you, is this a statement or not? So what is the meaning of the statement? A statement is a declarative sentence which is either true or false. Okay. Is it a declarative sentence? Yes or no? It's a declarative sentence, yes? It tells you a plus b to power 2 is equal to a squared plus 2ab plus b, declaring something. But is it a statement or not? Yes?
I think it's a predicate.
It's a predicate. It's very good to tell. Because usually in lower level courses, you call this a statement. And I just write this one and I say, is it true or false, by the way? Is it true or false before having this course? Is it true or false before having this course? It's true, yes? So, because we use it in Math 2C a lot. But this is, in principle, technically speaking, this is not a statement because we don't know the values of A and B, yes? So, in principle, you should write for all A and B in R, this is true. Then this is the statement. In lower level courses, we didn't write these things, but we meant this. So this is why this is a statement. Is it true or false? It's a true statement because we were able to prove it. Okay, if I want to prove it, what should I do? We have it here. So this is the universal quantifier. We want to prove it. So we need a valid argument. Okay, so in this case, if I want to prove it, how should I prove it? I would say that if you want to be very precise, you would say that let A and B be real numbers. Okay, then, so what I have, I start from the left-hand side, which is A plus B to the power of 2, and then I know what is the meaning of the power of 2. Here I am using a definition. So what is the definition of a number to power 2? It means, yes? It means the number multiplied by itself. So you see, I am bringing a proof, a valid argument for you. But what I am using my definitions and my previous knowledge that I know about numbers. Okay, so A plus B to power 2 by definition of power 2 means this. And then I use distribution law, so I multiply A by A, becomes A squared plus AB plus BA plus B squared. And then I know that these two numbers are the same because it doesn't matter if I multiply A by B or B by A. So these two numbers are the same. I'm adding them up, so it becomes 2AB, yes? Yes? And then I would say this is the right-hand side. This is called a direct proof. What is a proof? If I want to say what a proof is in mathematics, I can say it's a process through which I can show a statement in mathematics is true. That process is called a proof. And that in that process, I need to use my definitions, my previous statements that I know they are true. I can use them. Okay, so that is called a direct proof. I started from the left-hand side and then I proved that this is correct. Okay, now let me write another one here. Let me practice this. If I write this, is it a statement or not? This is a statement or not? It's a declarative sentence, but it's not a statement. It claims that A plus B to the power of 2 is equal to A squared plus B squared. So it is declaring something. But because it has variables, yes, so it cannot be a statement. What is the name of this? It's a predicate. If I want to turn it to a statement, I need to use quantifiers, either the universal one or the existential one. So let me just use the universal one. Okay, now it turns out to be a statement. Do you agree? It is claiming something which I can immediately evaluate. Okay, so is it true or false? Is it true or false? Yes. Why? Because at least you know the true one is this one. So it seems that this shouldn't be true. But can I say that if I ask you if I ask you in the exam, is this a statement true or false? And motivate your answer, you might think in this way. You might say that, okay, this is false, so far so good. And then you motivate your answer like this. You would say, because the true one is this one. Yes, we know from Math 2C that the true statement is this one, so this should be false. Then you will not get the points. Is that understandable? Is that clear? Because you cannot say that because the true one is this one, so this is false, because it is not the same thing, or it doesn't look like the same thing. Okay? And by the way, this is true, this one and this one don't look the same. Yes, but they are equal. Okay, so that's important. So if I ask you, is it true or false? You will say false. So you get, for example, 1 point. And for motivation, if you want 1 point, if you say, because the true statement is this statement and this one is not that one, so it is not true, then I will not give you that point. Yes? Because now you learned. If you want to refute this, you have to respect the rules. To refute a universal quantifier, what should I do? I need to bring an example that it does not work, which is called a counterexample. So if you want to refute this, you need to bring a counterexample only. There is no other way. Okay, so now, do you think I can bring a counterexample here? You would say this statement is false since, for example, let A to be 5 and B to be 2. Then A plus B to power 2 is equal to 5 plus 2 to power 2, which is 49, but A squared plus B squared is 25 plus 4, which is 29, and 49 is not equal to 29. So this is what you need to write down, okay, for the motivation. Is that clear? Yes. Okay, let me test your understanding again. So I will actually take that one off and write this quantifier for you. So there exists A, B in R such that A plus B to the power of 2 is A squared plus B squared. Okay, first of all, is this a statement or not?
Yes.
Yes, it was a predicate before, but I put the variables under a quantifier. So it turns into a statement. But then I can ask, is this a statement true or false? And again, you have to develop some intuition. And these, I will keep the examples simple. Because the point is not to do hard algebra. The point is just to understand what are these symbol meaning. Okay, so is it true or false now? They're very similar to the previous one, but I changed the universal quantifier to an existential quantifier. Okay, so now I'm asking you, first of all, is this a statement true or false? Then we will see what to do later. True or false? You say it is true. The previous one was false. This one you are claiming to be true. So that is this is existential quantifier. You are claiming that this is true. Okay? To prove it, we need to bring an example that works. Okay? By the way, it's not hard. You don't need to memorize those lines. Isn't it natural? You can come up with the same ideas yourself without even referring to those sentences. Is that clear? This is claiming that. Let us forget about those sentences. There are real numbers A and B so that it works. And you want to show that, yes, there are some numbers, so you have to bring example. Yes? It's not claiming for every number. It's claiming there are numbers A and B so that it works. So as soon as you bring those numbers, we are done. Yes?
A is 0
If A is 0,
and B is 1.
so you will say, so let me write it completely. So you say that this statement is true. Is true. Since, for example, if, okay, now I wait for you. If what?
If A or no, if A is 0 and B is 1.
And B is 1. Then, okay, A plus B to power 2 is, I will use your numbers. 0 plus 1 to power 2 is 1 to power 2 is 1. And A squared plus B squared is 1, 0 to power 2 plus 1 to power 2, which is 0 plus 1 and 1. Yes? And 1 is equal to 1. Yes? So this is the way of writing. I'm not saying that exactly follow my words or my sentences, but the structure more or less should be the same. So first of all, if I ask you, is it true or false, you need to clearly show me what do you think about it. Okay? So you should say the statement is true, and then you have to bring the argument. The argument might be an example or might be a valid argument, depending on the quantifier that you are using. Is that clear?
Yes.
Okay. So there are some other words that the book is introducing here. Let me also discuss about that. These are, the lesson is more or less finished, but I want to introduce you more definitions. So in mathematics, we have a word called axiom. So what do I mean by an axiom? Axiom is also a statement which we accept it is true without proving it. Okay? Because in principle we cannot prove everything. Yeah, we have to accept something and then we construct our mathematical knowledge based on the acceptance of some statements. Those statements that we accept to be true without bringing a proof, it's called an axiom. Okay, for example, a good example in the book is this. For all A and B in the set, of course they haven't mentioned like this, but now you're familiar with these symbols. For all A and B, yes, in R, if A is equal to B, then B is equal to A. Yes? Or if you don't like these symbols, let us just say that. For every real numbers A and B, if A is equal to B, then B is also equal to A. Yes? This is a statement, do you agree with me? And so it might be true or might be false. But we don't have any proof for that. It might be because it is so trivial for our brain. Okay? Of course, it doesn't mean that you need to take all the trivial things to be true. But anyway, this is one of the axioms that we use in algebra. We say that a number A is equal to B. I am allowed to conclude that, of course, B is also equal to A. It declares something. It might be true or false, okay? But we accept it to be true without any proof. That is called an axiom. Okay? Is that clear? For example, another axiom, it's probably a little bit better. So I would say for all A, B, and C in R, okay, I don't read it, you can read it for me, okay? So let me write it like this. If you don't know this symbol means and. This symbol means or. It's good to know these symbols, okay? Okay, now, is anyone who wants to read it for me now? In plain language, in plain English, okay, so how do you read it? Yes?
For all numbers A, B, and C from the set of real numbers.
So instead of this one, let me correct you right now, okay? I would prefer to say for all real numbers A, B, and C. It's better English one, yes? So for all real numbers A, B, and C,
Then A equals to B and B equals to C, then A equals to C.
no, you forgot one word. You didn't say if. So you should say if, yes? For all real numbers A, B, and C, if A is equal to B and B is equal to C, then A is equal to C. Yes, is that right? So this is one of those axioms. So we accept that this is true. If a number A is equal to B and B is also equal to another number, we accept that A is equal to C. Okay? That is called an axiom. There is another word very similar to axiom, that's called postulate. There is a delicate difference between postulate and axiom. Okay, so axioms are used usually in mathematics, postulates are usually used in other parts of science. So for example, postulate is a statement that we accept to be true for the sake of argument. Okay, so we say that let us assume that this is true, let us explore the consequences. So for example, in physics, if you are studying Newtonian mechanics, so for example, you say that so this is an axiom, for example, in Newtonian mechanics, okay? Of course, in physics, you call it second law, but here you can say second postulate of Newton. Yes? What does it mean? When you call it because when you call it axiom, by the very definition of axiom, it means you cannot refute it ever, because you are accepting it to be true. Okay? But here, when you say F equals to ma is a postulate of Newtonian mechanics, it means that I cannot be 100% sure that it will remain valid forever. Okay, so we say postulate. So usually postulate and axioms are the same thing. Axiom is used in mathematics, postulate is used in other parts of science. Yeah? When you say postulates of quantum mechanics are these statements, it means that somehow you might agree that sometime in the future they might be refuted. Okay? But axiom is more or less like the laws of the chess. If I give you the rules of the game will be the same millions of years from now. If you respect the rules, you can still play chess. It's more or less the same thing, yes?
Is established formulas in mathematics axioms? Like
No. Pythagoras theorem is called the theorem, you call it. Okay? So axiom and theorem have something in common. Let us explore them. Axioms are statements, theorems are also statements. Okay? Both of them are true statements, yes? But here we don't prove that they are true. Here we have to prove that they are true. So if you see theorem in a math book, immediately after that you usually see proof. So it means that I am proving that what is claimed in this statement is true, and I have to show it. Yes? Is that clear? Because I cannot prove everything. I have to accept something and prove everything based on the acceptance of those things. Yes? For example, here, I cannot prove that if A is equal to B, B is also equal to A. But it is very intuitive, we can accept it as an axiom. And then, in the proof that I want to express for a theorem, I should use only my definitions and axioms and the theorems that I have already proven to be right. So if I want to bring a proof for a theorem, the things that I can use here are, of course, logic. I can use my logical arguments, and then I can use my axioms that I established before, and I can also use the theorems that I showed them to be true before this very theorem. Okay? Is that clear? Could I answer your question? Yes?
Are there more complicated axioms than just equals, like A equals B?
No, in Euclidean geometry, for example, we have different axioms. For example, if you have a line, if you have 2 points, you can draw one line passing through them, and that line is unique. So this is intuitively clear for us, but we cannot prove it with simpler arguments, based on simpler arguments. So we accept it as an axiom of Euclidean geometry. Yes? That is a little bit more complicated than that one. But of course, the axioms in nature, first of all, the number of axioms that I establish for my theory should be as low as possible, the number of them, okay? So I cannot accept all of the axioms in the world and say that I accept all of them, then there is nothing left for me to prove, okay? So the number of axioms that I use should be minimal. And of course, they should be somehow intuitively correct. Because how we learn mathematics, by just looking around us, we try to see what is intuitively correct. If we can prove them, that is a theorem. If we cannot prove them, we accept them as an axiom. So an axiom shouldn't be very strange thing in practice. Might be if you are working in higher mathematics, they have very strange axioms or something like that. But then they will explore the consequences of those axioms. Yes? So that's the same thing. So the number of axioms should be minimum. So we want to make the minimum. So if I have 3 axioms and the other axiom can be deduced from the previous one, so we eliminate the last one. Yes? So that's what I'm saying. So this is the case. So that terminology I want you to know, and I think we are more or less done. Let me see if I have done something that we need to complete. No, there is nothing left, but there is one good example here. Let us also discuss about that. The problem, if I can translate it, is here. So if you have let us assume that you have a rectangle. Now let us say that the height of the rectangle increases by 10% and its width decreases by 10%. Yes? The height increases by 10% and the width decreases by 10%. Then the area decreases. Okay? So, first of all, do you agree this is a statement? Yes? It is declaring something. You have a rectangle. If the height is increasing by 10% and the width is decreasing by 10%, then the area decreases without any number for percentage of the decrease. So this is a claim. So we need to show if it is true or false. So then again, it's up to you to decide if it is true, prove it. If it is not falsified, refute it. So what do you think?
Could you repeat the question?
The question is this. The question is that I have a rectangle. The length is increased. Length is increased by 10%. The width is decreased by 10%. Claim, what is it claiming? Claim is that the area, I don't know what is the claim, but they have asked, yes, the claim is that the area decreases. Is it true or false? If you say it is true, then you understand that you have to prove it. You cannot bring numbers and examples, yes? Because when I say that I have a rectangle, how many rectangles are there? There are infinitely many. So, and this statement means for every rectangle, if the length is increased by 10% and the width is decreased by 10%, then the area decreases. What kind of quantifier is used here, even though it is not that mentioned clearly? But what is your understanding when I read this statement for you? Is it a universal quantifier or an existential quantifier? Yes? Universal. Because it says that for every rectangle, even though it was not mentioned even in the problem itself, they haven't used this phrase for every rectangle. But when you read the text like this, you understand it yourself. For every rectangle, if the length is increased by 10% and the width is decreased by 10%, then the area decreases. So this is a universal quantifier. So we want to prove it. You have to have an argument for it. If you want to refute it, then of course you might come up with a very simple example of one rectangle that this does not work. Then of course I agree with you there. Okay, which one do you think is correct? Do you believe this is true or false? Of course, in this problem you don't need to worry about. They are stating that it is true. So it means that you have to prove it. Yes? Because they have mentioned, show that or prove that if this happens, then the area decreases. So you don't need to judge for yourself. You have to go for a proof. But the proof, I don't know, how do you write the proof? You see that the problem is extremely simple. This can be done in Math 1C or even Grundskolan. The whole point is not solving the problem. The whole point is how to write the proof. Yes?
if you have 1.1a times 0.9b, it's always going to be 0.99
Mm.
ab. So the area is always decreasing by 1%.
Okay. Okay, but if you write this, I will not accept it 100%. That's completely true. I understand what you said. But you need to, because when you want to introduce you need to say that, consider this is the correct way of writing. Consider a rectangle of length L and width W. Okay, so this is important, by the way. If you just write L and W, or what you said B and H or whatever, without saying what B is or what H is, this is not a correct way of writing. Even though in English we know L stands for length, W stands for width, but I have to introduce, so don't hesitate to write words. That is, by the way, this is the important thing. The first part of this course is talking about proofs, so you have to be precise. So if you are using letters, you shouldn't rely on my judgment about I will know what does it mean. You need to introduce the letters, okay? So I would say that consider a rectangle of length L and width W. So then what happens? The area A will then be LW, yes? Something like that. Okay, now what has happened? L has increased 10%, yes? L increases that 10%. So this means that the new length L prime, for example, is equal to L plus 1 over 10. So let me write decimals. 0.10 L. Is that understandable? You see, it is clear. First of all, you introduce what L is, what W is, and what area means. Okay, so the area will be this. Now, this statement, L increases 10%, implies that the new length is L prime, which is the old L plus 0.1 L. Yes? Which is equal to what? 1.1 L. Yes? And then you can say that W decreases 10%. Then what happens? This means that the new width is W prime equals to the old W minus 0.1 W, which is what? 0.9 W. Yes? So if a person reads this, they will understand what you are doing. Yes? And then, therefore, the new area A prime is equal to L prime W prime. Yes? But what is L prime? L prime is 1.1 L multiplied by 0.9 W. Yes? And then if you multiply these numbers, becomes what? 11 times 9 is 99, and then you have 2 decimal points. So it becomes 0.99 L times W. But what is L times W? L times W is A. So this becomes 0.99 A. Yes? So you see, the new area A prime is equal to 0.99 times old area. So this means that the new area is smaller than the old area. Okay, so it means that yes, the claim is correct. Yes, the area decreases. Yes. And this is smaller than A. So A prime, which is equal to L prime W prime, is equal to 0.99 A, which is less than A. A prime is the new area, is less than the old area. So we were able to prove this. Yes? This is the correct way of writing a proof. So you see that in my proof, I have to use words, English sentences to, for example, don't hesitate to write therefore, hence, thus, or something like that, because you are talking to me, okay? Some part of it is expressed in symbols, but it doesn't mean that everything should be in symbols. What you think, you have to write it down, okay? So for example, let me try to, okay, so for example, if I go to, this is the platform that mathematicians, physicists, and computer scientists publish what they do research, and that's for free. For example, let us just pick randomly something in, I don't know, algebraic geometry. I even don't know what the article is, but let me just click on it. Okay, so this is a research article done by a, oh, sorry, thank you for telling me that. So this is a research article done by a mathematician, and that's a recent article, yes? Now you can see it? Yes. So let me make it a little bit bigger. Okay, so you see the first page, it includes a lot English words. So it's not exactly just formula. So that's only probably formula that you see here. So you see, that person doesn't write f sub p, even though all mathematicians know that p is usually standing for a prime number. But this is writing, suppose p is a prime number. It is introducing what's the meaning of this p he's using, or she is using, I don't know, okay? So they cannot just write this formula and then say that, okay, you are working in our field, you know what's the meaning of these things. Of course, here, he hasn't discussed about this because probably in his field, this is very famous, okay? But, and then, for example, then you continue, you see that how many English words are there, the formulas are actually very minimal, yes? So take this off from your head that everything should be written in symbols and everything. So these are the things that you need to know. So you see, all of it more or less written in words rather than mathematical formulas. Okay. Any questions? Okay, now you can work on the PDF file, so I will update which pages to read and which exercises to do. I really recommend you read the text. When I say study these pages, even though it's more or less the same what I told you here, it's very important to read the math text, at least very briefly, to review what's happening and then do the exercises. Okay, any questions? Thank you.